Today we would like to present you the COVID detector, which basically is a proof of concept to use complex machine learning technology and apply it to a complex biological system to get detected, and also for the diagnosis and in healthcare. So basically, this is our content. So we would like to give you a small introduction about respiratory diseases, how is diagnostic treated, what is the impact of these illnesses. We will talk about the data structure and the data source we have used for this approach, and also how to apply deep learning to this specific problem. We'll talk about results we get and also the limitations and how we can improve the scope, and also to put this approach in perspective to diagnostics approaches in general in healthcare. So now I would like to give the words to Sujit.
Hi, thanks, Paul. First, I would like to thank everyone for the last great 3 months, exciting learning, having lots of fun here. So I'll just talk about what's going on in the world, which obviously everybody knows that the pandemic has hit us really hard. But even before the pandemic, respiratory diseases are very, very highly prevalent in society, in the world. And if left untreated, obviously they will cause lots of serious damage. Lots of other diseases apart from COVID, like pneumonia, bronchitis, tuberculosis have been existing and devastating populations all over the world. And it has been very serious, especially for countries like India and Africa. Would it be possible to distinguish symptoms just from the symptom, whether it's a serious one or just a regular symptom? So this is what we've been thinking. And in general, the business case was that COVID has been very devastating. As of today, almost 250 million cases have been reported, and around 5 million deaths have already been reported so far. It has devastated society in many, many ways, and almost 95 million people more went into extreme poverty last year, and around 80 million have been very undernourished and compared to pre-pandemic levels. So things are bad, and so the motivation for this project is that even though we can do tests in cities and the Western countries, rural areas are still suffering because there's a very low healthcare resources available, and it's very difficult to assess the symptoms. And pre-screening tools would be very useful to prioritize cases and reduce the load on the healthcare providers. So what would happen if we could have a tool which anybody can use, and it's in a phone and accessible to everybody in rural areas? So getting medical data is really hard. That's a big problem because of privacy reasons. Clinical trials are expensive. Getting the exact kind of medical data is not something that we can do as normal people. Healthcare institute or hospital, government has to be involved. So that was very hard for us to just get data related to respiratory diseases. So luckily, the Indian Institute of Science in Bangalore, which is akin to the RKI in Berlin in Germany, like the Robert Koch Institute, it's the premier health organization. They started a project called COSVARA, which lets volunteers log in and record their own respiratory data with a questionnaire. At the end of the presentation, you can see how you could possibly contribute to this. And we were very lucky to have this small data set available, and that's what we used to try out our project. So the data source is basically sound data on 9 features like coughing heavy, coughing shallow, breathing heavy, deep, stuff like that. They're all given as WAV files, which are recorded by volunteers. So they are very different in terms of quality from each other. That's one of the problems. And the data set that we had was very unbalanced because only 56 corona positive cases were there in more than 1,300. So this was a huge problem for us to work on this. But yeah, we found a very unique approach to solve this problem. And the challenges we had to this product through this project, well, there were missing data which had to be taken care of, which is very important for any data project that you work on to start looking at that before. Then we had some nested structures, and normalization and reshaping the data was a big problem because all kinds of different sound files of different sizes and qualities were there, and we had to figure out how to make some kind of normalized sense out of it. And the last problem was the quantity. We would like to have a lot more data to make something commercially usable. And with that, I will invite Paul Tomek to talk about our deep learning approach.
Hello, guys. Yeah, let me get into the technical part of how we approached it. So after some analysis, talking, consultations, we came to the conclusion that we should treat this problem as an anomaly detection problem, and that already narrowed down a little bit the scope of models and approaches that we can. So to solve this problem, we picked variational autoencoder as the tool that will be most likely to help us and solve it. So what is a variational autoencoder? To give a deep explanation would need some more time, but talking generally, it is built out of two different models, one encoder and a decoder. The first one learns to represent an image into a latent space, and the second one, decoder, takes this latent space and out of it generates a reconstructed image. So our approach here was to train the model only on healthy cases, so only on data from the healthy people, so that the model knows how to reconstruct the healthy sounds, and then test it on a mixed data set of healthy and unhealthy cases, with an assumption that it will do much better reconstructing healthy cases compared to unhealthy, and those would be treated as an anomaly. Yes, here we can see a little bit of a pipeline of how the data was processed. We started with wave files audio data, which were converted into mouth spectrograms. After some manipulations, reshaping, we converted them into tensors and fed them into the model, which doing the whole loop of encoding and generation gave us reconstruction as an image. Our approach here was having this reconstructed image, we take it and compare it to the input. So we look at both the input and the output and look at the differences. How, if the difference is bigger, we assume that it's an anomaly. If the difference is smaller, we assume it is a healthy case. Now Paul will talk a little bit about the results of how we did.
So I will take you through the results. Basically, here you can see that we trained our model like it is normal did in machine learning, like generating a training and a test set. Here we made a train validation split of 80% to 20%, basically meaning that we are training on 80% of the training data and uses 20% for a validation, just to see if we are able to train a model in a proper way, if we are overfitting it or not overfitting it, so that we have some control about the machine learning approach. Sujit said already that we have a very complex data structure, and what we actually did, we have data from 9 different features. And the first idea was to see, okay, are we able to make for each feature a model and see which of these features, which is basically an attribute, for example, coughing heavy, coughing shallow, or breathing, might be important to generate an algorithm which is able to detect the positive samples. Personally, I was curious about which of this feature might perform better than the others, since also from the Kosvara project, it was not really clear which of these features might be have an impact on the machine learning models. So at the end, we were training our model with, we are creating 9 different models based on these samples. And at the slide, you can see an example of a training of a model in which we have used the coughing heavy data. So basically what you can see is that on the y-axis we have a loss number, which is indicating the construction loss, and basically what we expect during training that the loss will drop after epoch. Which basically means that after each iteration, the model is like learning and the reconstruction will be better. In this case, you can see a line in orange, which is the training data set, and in blue, the validation set. And basically, what you can see here is that the orange and the blue line is like dropping more or less the same. So we can assume that our model is training for the training set in a similar manner to the validation set. Okay, so next step would be basically to test our model in a prediction way on data it hasn't seen. So what was like the test data set we generated. And the test set generated, we generated in a way that we tried this time to make a balanced data set. So we took each 56 positive cases we are able to get out from our data and supplemented it like with 56 other healthy data. And then try to make a prediction and see if our models are able to catch and to detect in the right way. So what is the result? So now of the 9 models was able to predict with a higher accuracy of 60%. Basically, we're asking ourselves, okay, so what exactly happened here and why is this the case? And you have to, I would give you an example, which we call the coughing challenge. And basically, I would like to play you a sound so that you understand the challenge of generating a model from this kind of sound data. So you hear now the healthy cough. And now we can play a sound from a COVID patient. So what we can distinguish, so there is a difference, obviously, from both. But for the model, it's a really complex task because, as you can see here, it's not only the sound by itself, which is in a complex way different from each other, because we have this kind of breaks in which there are milliseconds of non-tone and then the sound of the cough. But even there's a much more complicated situation because each person has a different tone, different amplitude, different color of his voice. So when he is coughing, this is also causing problems, which is basically a very general problem if we are making diagnosis in healthcare, that we have taken a random sample, of course, but we always have to think about that each individual is different. And this is like putting noise into our system. So on the data side, what we can do, what are the limitations in the outlook? So the medical sound data are complex and inhomogeneous. This is the main reason or the main challenge for us. So the knowledge of sound characteristics and how to manipulate sound in a pre-processing step is crucial to detect the similarities and differences, which basically says that there must be a knowledge about how to treat a very specific sound sample. So like playing around with the sample size, with the length, with the sample rate, with window slices, and also the normalization and scaling. But there's also another side, which is like, I would say machine learning is not enough. Basically, domain knowledge is as important as machine learning skills to address complex diagnostics challenges in healthcare sector. We can see here that one feature is not enough to treat it with a machine learning approach and expecting to get out an approach which is detecting it in a very high accuracy. So basically, experts has to investigate which features are important, which symptoms are important to look at. Must there be engineering or re-engineering of the features? Which features we have to select and extract, but also how to combine features, for example. And this would also be for us, for our COVID detector, a perspective in which you would say, okay, so we have not only to work on the sound, but also to have to think about how we can combine features, how we can implement multiple features in the model to improve our COVID detector. So in summary, what does it say? Machine learning can be a very powerful method also in healthcare and in diagnosis. But at the end, it's also important to have the experts, the people who are doing the clinical trials to provide us data which are meaningful. And also people like who are working in laboratories. And also the physicians who have to treat and to interpret like symptoms and give a hint which might be important and which not. So I would close our presentation. I would special thanks to our mentor Tristan and also Mohammed, who was doing a lot of coding work and helped us really a lot to make even this baseline. Because, as Tomek said, we were struggled and very often and in different points, and he was very helpful. Of course, I would like to thank the whole DSR 27 batch for fantastic 12 weeks in which we learned, we were laughing, crying. So thank you very much for this great journey and great experience with you guys.